This is the second part of my lecture series. It actually has exactly the same name, also here, quantile and distribution regression models. What we should realize is that we have already looked at quantile and distribution regression models, but the models that we have looked at so far were quite standard. We could essentially compare them to the standard linear regression model that we know from, well, the beginning of econometrics. In that sense, we haven't looked at all at, for example, things as endogeneity, but also we haven't looked at other problems, such as the fact that the left-hand side variable, we have assumed it so far to be completely continuous and to have, well, potential outcomes from minus infinity to plus infinity. Well, that might not be true. We know already from standard econometrics that we, for example, could have a binary regression outcome. We could have a situation in which the, say, left-hand side variable, the outcome variable, can only take values equal to 0 and 1. And the question, of course, arises, could we take that also into account at the moment that we're going to look at quantile regression analysis? Well, the answer to that relatively simple question might be that maybe not. It may be possible that we are not able to do anything with respect to quantile regression at the moment that we are going to have a binary outcome variable. And the reason behind that is because of the fact that, unlike what we have with respect to a standard mean regression model, we should realize that quantiles, at the moment that we're going to look at quantiles, we can only have, say, outcomes with respect to a quantile. Quantile always has to be equal to, well, a support point. So that means that if we have only outcomes equal to 0 and 1, well, then the quantile should also be equal to 0 and 1. The moment that we are going to have a population in which the percentage of zeros is more than 50%, then at the moment that we're going to look at the median then is equal to 0. And at the moment that the number of zeros is less than 50%, then it's simply the case that the quantile is going to be equal to 1. But that's going to be quite difficult with respect to regression analysis. The moment that we're going to look at standard regression analysis, then we do of course know that even in the case that we only have a binary outcome variable, then we can still do a standard linear regression. That's usually called the linear probability model. Of course, we can look at more difficult models, but standard linear regression still works. That's not the case at the moment that we're going to look at quantile regression. At the moment that we're going to look at quantile regression, we always have to adapt the model in such a way that we can take a binary outcome into account. That we're going to do over here, and we should realize that in the end it's not going to be that different from what we have in standard linear regression analysis. Let's introduce an outcome variable that we denote here by y1 star, and we're going to assume that in this case the quantile regression assumption is going to hold for this y1 star. So we simply are going to assume that the quantiles here at location tau of y1 star, conditional x1 equal to x, is simply equal to x times beta tau. So this is now going to be our relationship, well, if y1 star would have been observed, then we can just exactly do the things that we have done so far. But in this case, y1 star is going to be so-called latent outcome variable, and that means that it's actually not observed. So even though we're going to assume that, well, the standard assumptions, well, first of all, that y1 star is IID, but then what we're going to assume over here is that y1 star is unobserved. Instead, we only observe y1. And y1 is going to be equal to 1 in the case that y1 star is larger than 0, and y1 is equal to 0 otherwise. In the case, of course, that y1 star is smaller or equal to 0. We can write our model like this, but we can write an equivalent model in the following form that we've over here. We can also write y1 as being the indicator function that indicates that y1 star must be larger than 0. This is exactly the same model as what we have over here, because it's not so difficult to see that if y1 star is larger than 0, well then of course this thing is equal to 1, and then we end up over here, in this model over here, and at the moment that y1 star is not larger than 0, so smaller or equal to 0, well then this thing is going to be equal to 0, and then we end up here also at 0. So therefore this model is exactly identical to that model over there. But there is a benefit of writing it in this form that we have over here. And the reason behind that is because of the fact that if we are going to write in this form that we have over here, we could actually also then represent the right hand side in terms of a function. We could introduce the function gy, which is nothing else than the indicator function that indicates that y must be larger than 0. Of course, then in that particular situation, this y1 is nothing else as g evaluated in y1 star. But the reason to represent it in this form that we have over here is that we should realize that gy is a so-called monotonic transformation. It's well, we will see on the next slide, it's an increasing function. And remember that there is a relationship between, say, quantiles and monotonic transformations that we will discuss later. But before I'm going to do that, I'm going to first of all look at this function that we had in the previous slide. It's a monotonic transformation, and that's immediately clear at the moment that we're going to look at the, well, a graphical representation. Here we have on the x-axis we have y, and the function is here on the y-axis. Well, and even though this function of course looks a little bit strange, it's most of the times it's constant, but it has an upward jump here at 0. We should realize that whenever it changes in one direction, it changes upwards. So that means that this is a monotonic transformation. It's not strict, of course, but that is actually not necessary. And now remember that there was something that had to do with quantiles and so-called monotonic transformations. We do already know that in the case of quantiles, at the moment that we have a monotonic transformation, then, unlike what we have with respect to means, we can say that the quantile of a function is the function of the quantile. So that we can do here as well in order to get a relationship between the quantile of y1 and the quantile of y1 star. Let's look at the quantiles of y1, condition x1 equal to x. We don't know anything yet about this thing that we have over here. We've only made assumptions with respect to the quantile of y1 star. But of course we do know that y1 is nothing else as this thing that we have over here, so we can also write it as the quantile of this indicator function that we have over here. But now remember that, as I already said, at the moment that we have a monotonic transformation, and this is a monotonic transformation as we have seen in the previous slide, then the quantile of a function is the function of a quantile. So therefore we can also write this as the indicator function that says that the quantile of y1 star should be larger than 0. Well, this is actually a very nice representation because of the fact that now we are going to see that there is a relationship between, say, the quantile of y1 and the quantile of y1 star. Well, we can even go one step further and realize that we have made an assumption with respect to this quantile that over here because of the fact that we have assumed so far that this quantile that over here is actually equal to x beta tau. So therefore we can also write it like this. And this is actually extremely nice representation because of the fact that you should realize that what we have here at the left hand side, well, this is something that is identified. We should realize that both y1 and x1, they are observed. So therefore the quantiles of this thing that we have over here, that is identified. So therefore we should realize that at the left hand side we have here something which is identified. And then at the right hand side what we actually have is beta tau. And beta tau is actually the thing that we want to estimate. So we actually want to know whether this thing over here is identified. So therefore what we're going to see here is that we have here representation between the thing that is observed, this thing that we have over here, and the thing that we want to estimate. Maybe better in econometrics terms to say, we have here a relationship between the thing from which we know that it's identified, this thing that we have here at the left hand side, and we have a relationship with that of the thing that we want to identify, and that is this beta tau that we have over here. So this actually now looks like a nice relationship. Well, I would like to go back one step and look at this relationship then over here. On the next slide, I will give a graphical relationship in order to get a little bit more of an intuition. But we should realize that this is actually already quite intuitive. And the reason behind that is because of the fact that I've said earlier that, well, the quantile of y1 can only get two outcomes. It's either equal to 0 or it's equal to 1. There's no other potential outcome with respect to this quantile that we have over here. That's actually also what we see over here. Because of the fact that it's an indicator function, we can have here also just have two outcomes. Either we have a 0 or we have a 1, depending of course on whether the quantile of y1 star is positive or not. Well, then we can actually also see at the moment that we're going to look at this picture that is over here. Here we have on the x-axis we have the different values of y, and on the y-axis we have the distribution functions. And let's first of all look at the distribution function of y1 star conditional on x1. Let's assume that that is this distribution, this red distribution function that we have over here. Of course, we do not really observe y1 star, and well, y1 star itself actually even doesn't have any interpretation. But let's just assume that the distribution of y1 star is equal to this thing that we have over here. I'm going to do that because of the fact that I would like to then relate that to the distribution that the thing that we do observe, and that is y1. So the question arises, how is the distribution function of y1 related to the distribution function of this y1 star that we have over here? Well, for that, what we can do is that we can actually look, first of all, at values below 0. What is the distribution function of y1 for any value below 0? Well, the obvious answer to that question is it's equal to 0. And the reason behind that is simply because of the fact that y1 can only take two outcomes. It's either equal to 0 or equal to 1. So the probability that y1 is smaller or equal to anything below 0, well, that's of course equal to 0. We cannot have an outcome, for example, below -1/2. So that means, of course, that the distribution function evaluated in -1/2, that's equal to 0. So therefore, up till 0, we do know that the distribution function of y1 is simply equal to 0. But what happens at 0 itself? Well, then you should realize that the distribution function of y1 evaluated in 0 is actually nothing else as the probability that y1 is equal to 0. And the question, of course, arises, what is that particular probability? Well, before answering that, the first thing that we can ask ourselves is, well, what does it mean in terms of y1 star at the moment that we know that y1 is equal to 0? Well, if y1 is equal to 0, we know that y1 star must be smaller or equal to 0. So that means essentially that the probability that y1 is equal to 0 is equal to the probability that y1 star is smaller or equal to 0. And that's by definition, of course, equal to the distribution function of y1 star evaluating 0. And that means actually nothing else is that we get here an upwards jump towards the distribution function of, say, y1 star, because of the fact that we now know that although it was always equal to 0 so far, now we do know that the distribution function of y1 at 0 is equal to the probability that y1 is exactly equal to 0, and that's equal to the probability that y1 star is smaller or equal to 0, and that is of course equal to the distribution function of y1 star evaluating 0. So therefore, we get this upwards jump towards the distribution function of y1 star. Then the question arises, what is going to happen next? Well, next we should realize that in between 0 and 1, nothing actually happens. And the reason behind that is because of the fact that y1 cannot take values in between 0 and 1. For example, at the moment that we're going to look at the probability that y1 is smaller or equal to 1/2, well, that is exactly equal to the probability that y1 is smaller or equal to 0. Because of the fact that, well, there is no potential outcome between 0 and 1/2 with respect to y1 that over here. So therefore, up till 1, nothing actually happens. But then at 1, we're going to see that we're going to have another jump upwards towards 1. That's always the case. And that's also not that difficult to understand, because we should realize that y1 can only take two values. It's either equal to 0 or it's equal to 1. So therefore the probability that y1 is smaller or equal to 1 is actually equal to the sum of the probabilities that y1 is equal to 0 and the probability that y1 is equal to 1. And that is by definition equal to 1, because of the fact that it's the sum of all the potential outcomes that we have with respect to y1. So therefore, by definition, we get a, say, jump upwards always to 1. And this difference, of course, that we have over here is the probability that y1 is exactly equal to 1. Well, then after this 1, we are going to see that the distribution function of y1 is always going to be equal to 1. That also makes sense because of the fact that distribution functions cannot be larger than 1, and they can also not be decreasing. So therefore, we get always this pattern that we have over here. But now what we can do is that we can now look at the quantiles with respect to y1 star and with respect to y1. Let's start with the median. Then of course we have to start here another time at 0.5. Then for y1 star we have to go all the way here, and we go down then here, and here we are going to get our quantile of y1 star, our median of y1 star. Well, we should realize that at the moment that we're going to do then the same with respect to y1, then we have to go a little bit further because of the fact that then we have to go all the way to this blue distribution function. We're going to see then that the quantile of y1 conditional x1 equal to x is equal to this thing that's exactly equal to 1 over here. And that's in line with what we have seen at the previous slides. We have seen at our previous slide that, well, at the moment that the quantile of y1 star is positive, that's the case here because of the fact that we are here from the right of 0 with respect to the quantile of y1 star. Well, then it should be the case that the quantile of y1 must then be equal to 1. We will see exactly the same thing at the moment that we're going to look at the third quartile. The third quartile for y1 star must be by definition larger, and because of the fact that the quantile or the median of y1 star was already positive, that means that of course for the third quartile it should also be positive. So therefore we are going to see that the quantile of y1 star is positive, and we also see that the quantile of y1 is equal to 1, which again of course is in line with what we have seen earlier, that at the moment that the quantile of y1 star is positive, then the quantile of y1 should be equal to 1. But that's not always the case. We could also look at the first quartile. So then we're going to here look at 0.25, and then at the moment that we're going to go all the way to the red distribution function, then we see that the quantile first quartile of y1 star, it's negative in this case. We are here now from the left of the 0 that we've over there. And then we're going to see that at the moment that we're going to look at the quantile of y1, well, that is then equal to 0. Again, that is in line with what we have seen before, because now we have a negative quantile for y1 star, and that implies that, well, our indicator function now indicates that this must be equal to 0. Well, what we immediately see is that at the moment that we are going to go to below of 0.25, then the quantile of y1 star is even going to be smaller. So it's still going to be negative, of course. So then also the quantile of y1 is going to be equal to 0. The moment that we're going to go up, well, if we go up a little bit, we will still see that the quantile of y1 star is going to be negative, and that the quantile of y1 is going to be equal to 0. But there is, of course, a point somewhere here, around 0.40 or something like that, for which we are going to, well, have that the quantile of y1 star becomes positive. So if we are going to go then in that direction, it's going to become positive, and that means, of course, we have here, well, a jump in terms of the quantile of y1 from 0 to 1. So there, for the low values that we have over here, we're going to see that the quantile of y1 is equal to 0, but at the moment that we are going to be higher than this value that we have over here, then we are going to have a quantile equal of y1 equal to 1. Okay, I would like to go on, and I would like now to go on with the estimation of the binary quantile regression model. In that sense, it's good to remember that we have already seen that any kind of quantile, actually including, I haven't said that at that moment in time, but including that those that are discrete, for which y1 is discretely distributed, we do know that the quantile of any random variable, in this case y1 conditional x1 equal to x, can be represented by the argument that's going to minimize this function that we have over here. That's, as I already said, also true in the binary outcome case. So we still have this relationship that we're over here. And then the first question that we can ask, what is then the minimum outcome that we can actually have with respect to this function? Well, that is very standard mathematics, of course, because of the fact that that's something you already know from high school. Only thing that we now have to do is that we simply have to substitute into the minimum of this function that we're over here. We have to substitute it in order to get the lowest potential outcome. So therefore this now is going to be the lowest outcome that we have with respect to that function that we have over there, because we have simply substituted in the minimum. Well, now we should realize that we can rewrite this a little bit. We already have that we can write this now as this indicator function that we have over here, because we have already seen before that, well, the quantile of y1 conditional x1 equal to x is equal to this indicator function that we have over here. So therefore we can simply substitute that in. But then we should also realize that at the moment that we're going to look at this relationship that we have over here, that this is actually also the minimum outcome of actually another function, not a function with respect to the, say, quantile and with respect to the q that we have over here, but we can also do it with respect to the thing that we have over here. You can also realize that beta tau is now going to be the argument that is going to minimize this function that we have over here, because of the fact that you should realize that if we're going to minimize now this function that we have over here, and we then substitute it in over there on the previous slide, then we also get the minimum outcome with respect to that particular function. So therefore we should realize that we can also write it in the way that I have it over here. Well, now what we can do is that we can use tricks as what we have already seen before. What I would like to do now is that I would like to write this say minimum function that we have over here. I would like to write this just as one particular integral. We have two integrals, but I would like to write it now as one integral. We have already seen that that's not that difficult. The only thing that I need to do is that I have to make the area of integration here and there exactly identical to each other. And well, if I take the union, then I simply have the support of y conditional x. So therefore I can here integrate over the total support of y conditional x, but then I have to take into account, of course, that I need here an indicator function. I have to take into account that this can only be different from 0 at the moment that y is going to be larger than this indicator function that we have over here. So therefore I'm going to get an indicator function that actually, well, it's over here, that's going to indicate that y must be larger or equal to this indicator function that we have over here. This looks a little bit bad because now we have an indicator function within an indicator function, but that's what it is that we have right now. We can do it with respect to the first integral, as I've just done, but we can also do it with respect to the second integral. Then we have to realize that if we're going to integrate over the full support, well, then we have to have an indicator function that indicates that y must be smaller than this indicator function that we have over here. So in total we can write it like this. Now we have two integrals, but we can now take them together. And that's what I've done now over here. Now we have an extremely long, say, integral. It starts here at this line and ends actually over there. But one thing we can do is that we have very long parentheses here as well. But what I can do is that I can at least take the densities that we have over here, I can take them out of the parentheses. So then what we're going to get is now this relationship that we now have over here. Well, and then the next thing that I can do, well, this is actually already what I more or less wanted, but the next step that I can do is that I can realize that this actually holds true for any x. So that means that I'm going to look at two different x's in, of course, the support of x1. Then, given the fact that this thing always is going to be positive, well, given that particular fact, I can realize that if I'm going to, say, sum up the minima with respect to this thing over here, then actually it should also have been the total minimum. So there we should realize that we should also have that if I'm going to sum up over two different x's, then beta tau should also be, say, the minimum of this particular sum, because of the fact that it's going to minimize with respect to both, say, the elements that we have in the sum. We know, of course, that summation is exactly the same as integration, so therefore we can also do it with respect to the very long integral that we have over here for all the, say, support points that we have with respect to x1. And then what we're going to have is that we're going to have exactly this function that we have here inside the integral, and we are going to integrate now with respect to the different values of x that we have over here. So then we get this whole, say, function that we have over here, and beta tau should actually also minimize this function that we have over here. But then we see here that we have here a conditional density multiplied by marginal. Can take them together, because we do know that a conditional distribution multiplied by marginal is actually also equal to a joint density function. So therefore we should realize that we can actually also write like this. And this is actually a very nice way to represent it. The reason behind that is because of the fact that now what we do is that we are going to integrate now over the full support of x and y, and we do that with respect to density function. That means, of course, that this thing over here is nothing else as a population mean. It's the population mean of this whole function that we have here in between parentheses. That means that we can also write this as a population mean. We get an e, of course, for the population mean, and then we only have to replace these y's, these little y's, by y1, and the little x's by x1. And then we get this relationship over here. This is, of course, a nice relationship because of the fact that it now says that if we would have known this function that we now have here at the right-hand side, well then, at that moment in time, the only thing in order to get beta tau is to minimize this function with respect to the b that we have over here. And then we get beta tau. But that's, of course, not possible. The reason behind that is because of the fact that we should realize that we do not know this function over here. We can only know that function at the moment that we know the joint distribution function of y1 and x1. Generally, we do not know that. So therefore, we can actually not, say, calculate this thing that we have over here. But one thing we can do as econometricians is that instead of using here the population mean, we can try to estimate it by the corresponding sample mean. So what does that mean? Well, that means, of course, no expectation, but we're going to have summation. We're going to sum over all the observations that we have over here, and we divide by n in order to get this thing that we have over here. And now we should use the law of large numbers to realize, of course, that this thing that we have here now at the right-hand side is going to converge to the thing that we have over here at the right-hand side for any level of b at the moment that n goes to infinity. It converges, this thing over here converges in probability to this thing that we have over here at the moment that n goes to infinity for any level of b. That means, of course, that this function that we have over here, it's a function of this b that, of course, that we have over there, is exactly identical to that function that we have over there at the moment that n goes to infinity. Well, if two functions are exactly identical, then they should also have their same minima. So that implies, of course, that this function over here at the moment that n goes to infinity, the minimum of it is exactly equal to the minimum of this function that we have over here. And that is, of course, by definition equal to beta tau. So therefore we should realize that at the moment that we're going to define beta hat tau as being the minimum of this function that we have over here, well, generally, of course, beta hat tau will be different from the beta tau that we have at the previous slide. What we should realize is that if n goes to infinity, then the minimum of this function over here is going to converge to the minimum that we have over there, and that is by definition equal to beta tau. So hence, beta hat tau is also going to converge in probability to beta tau. And that means, of course, that the beta tau that we have over here is now going to be a consistent estimator of beta tau. So that is actually quite nice. We can also write this a little bit differently by simply, well, defining a particular m function that we have over here and say like, well, beta hat tau is nothing else as the argument that's going to minimize the sum of this m function that we have over here. Where of course m, the function m, is now defined as this function that we have now over here. But this looks pretty difficult. This looks, I would say, even quite horrible because of the fact that we have here even indicator functions within indicator functions. So therefore we should realize that this doesn't look so nice. But we should realize as well that actually yi can only take two values. It's either equal to 0 or 1. So therefore we can ask ourselves the question, can we actually rewrite this function a little bit at the moment that, for example, yi is equal to 1? Well, then the first thing that we can do is that we can simply substitute in here ones for wherever we see yi. So we can actually then write it the way I've done over here. Well, this doesn't seem to help that much, but we now should realize that if we're now going to, for example, look at this indicator function over here, what does it now say? Well, it says that 1 should be larger or equal to an indicator function. Where an indicator function, of course, can only take values which are either equal to 0 or 1. So this logical thing that we have now over here actually is either saying that 1 is larger or equal to 0. Well, that's of course always true. But we should also realize that if this thing is equal to 1, then we have here 1 is larger or equal to 1. That's actually also true. So that implies that this say logical operation that we have over here is always true. So that means that this say indicator function always will indicate to 1. So that means that we can actually delete this part over here because of the fact it's 1 anyways. Then the question arises, what about this indicator function that we have over here? Well, that says that 1 is strictly smaller than an indicator function, where we should realize, of course, that again, that indicator function can be either equal to 0 or 1. Now the question, of course, arises, when is 1 smaller than, well, at the moment that this thing is equal to 0, when is 1 smaller than 0? Well, that's of course never true. But we should also take into account that 1 is never smaller than 1 itself, because it's exactly equal to 1. So therefore we should realize that what we have over here, this logical expression that we have over here, well, it's actually always untrue. So therefore we should realize that this thing that we have over here is always equal to 0. So that means, of course, that this is equal to 1. This whole thing is equal to 0, so we can completely delete it. And that means, of course, that we can also write this m function now as this thing over here. We can also look at a situation in which yi is equal to 0. And of course we need to substitute in here zeros, as I have done over here. You may of course say like, well, but you had here minus signs in front and you don't have them here anymore. But that has all to do with the fact that I also have deleted here the absolute value. You should realize that if I'm going to have here deleted this yi because of the fact that it's 0, then I get something which is either, well, 0 minus 1. Taking absolute values, of course, I can delete, in fact, the absolute values together with the minus sign. So therefore, we don't have a minus sign over here, we don't have it over there. Now another time we can look at this indicator function over here. Here the indicator function indicates that 0 must be larger or equal to something that could be equal to 0 or 1. Well, of course, if we have here a 1, well, then we have 0 larger or equal to 1. That is, of course, not true. So then this thing must be equal to 0. But we can also have that, well, this thing that we have over here is equal to 0. Then we have 0 is larger or equal to 0. That's actually true. So that implies that if this is equal to 0, then this indicator function is equal to 1. But when is that true? Well, that's of course true in the case that xib is not larger than 0, but it must be smaller or equal to 0. So there we can replace this whole indicator function by one indicator, which actually says that xib should be smaller or equal to 0. Here it's actually the other way around. Here we have that the logical expression is 0 is smaller than this indicator function. That's something, again, that could be equal to 0, 1. Well, at the moment that we are going to have a 0 in this case, if this is going to be 0, then it's untrue, of course. 0 cannot be strictly smaller than 0. But if in the case that we have a 0, 1, then we actually have here the logical expression is then 0 is smaller than 1, which is actually correct. So therefore here we can replace this thing over here completely by one indicator function that just indicates that xib is larger than 0. So therefore now we get this relationship that we have over here. This can still be rewritten a little bit, and the reason behind that is because of the fact that here we have an indicator function that says that xib is larger than 0. And here we multiply it by xib smaller or equal to 0. So you realize that always one of the two is equal to 0, because of the fact that if this is equal to 1, then that is equal to 0. And if this thing is equal to 1, then that thing must be equal to 0. So that means that this whole thing always is equal to 0. Here it's a little different because of the fact that here we have exactly the same indicator functions multiplied by each other. You could of course write this as the indicator function squared, but we already know that you don't have to do that, because squaring an indicator function just gives the indicator function itself. So therefore we can now in the end simply write it like this. So if y is equal to 1, we get this. If y is equal to 0, we get this relatively simple expression. We can combine that. What we can do is that we can now, well, write m as yi multiplied by this expression that we have over here. Then we get this expression over here as y is equal to 1, then we simply get this expression over here, plus 1 minus yi multiplied by that expression over there. If y is equal to 0, then we simply get this. And of course, if y is equal to 1, then we simply get this thing over here. We can still rewrite this a bit. What I can do is I can get rid of the parentheses over here. So I can write this as yi tau minus yi tau times this indicator function that we have over here. And the reason I'm going to do that is because of the fact that then I have here exactly the same indicator function as I have over there. So I can actually bring this term over here into parentheses that I have over there. So then we get now this relationship that we have over here. I can still further rewrite this. I can get rid of these parentheses over here. What I'm going to do is that I'm going to simply write minus 1 minus tau, and then what we're going to have is plus yi times 1 minus tau. So therefore I'm going to get this thing over here, and again even get rid of this parenthesis over here. This is of course equal to yi minus the tau of yi, so then we get this thing over here. And if these two things are going to be deleted against each other, then we're simply going to get this thing now that we have over here. And that implies in the end that what we can do is that we can actually use this function over here that must be minimized. That's actually, then we get to an estimator that is, well, already introduced in a Journal of Econometrics article by Chuck Mensky in 1985. And, well, what we're simply going to do is that we're going to, well, minimize the m function that we had at the previous slide. Well, if we just substitute that m function in from the previous slide, then we get to this function that we have over here. We can still rewrite this a bit because of the fact that we should now realize that this part of over here doesn't even depend on b. So therefore we do know that at the moment that we have something that doesn't depend on the thing that we would like to minimize on, we can completely delete it. So therefore we can also minimize simply by this term that's over here. If we're going to do that, then we are going to see that we have here a minus sign now in front. We do of course know that minimizing something which is with a minus sign in front is exactly the same as maximizing the same function, but then with a plus sign in front. So therefore, I can even write it like this. Well, now what we're going to do is that we're going to maximize this function that we now have over here. But before we're going to be able to do that, we should just say one additional thing with respect to identification. You realize that if I'm not going to make any restrictions with respect to the b that we're over here, then this thing over here is not identified. It looks very bad, or it sounds at least very bad, but that's not really the case. You should realize that even the probit model, a standard probit model, we could of course ask ourselves the question, why do we in a standard probit model actually assume that the variance of our normal distribution, take into account the probit model of course assumes that the error term is normally distributed, but we typically assume that the variance of that normal distribution it's equal to 1. Why don't we just allow for another value of the variance? So why don't we simply estimate the variance as well in the probit model? Well, the answer to that is simple. It's not identified. The reason why it's not identified is because of the fact that we have only two outcomes, 0 and 1. And therefore, unlike in the continuous case, the, say, variance, from which we of course define, it's not identified. If we are going to increase the variance from, say, 1 to 2, well then we can actually look at exactly an equivalent model by actually also multiplying the beta coefficients by 2. And the same problem actually arises over here. So therefore we need to look at a normalization. One of the ways in which I could have looked at normalization is just to set one of the beta coefficients simply equal to 1. I'm not going to do that here, at least Minsky didn't do that. He actually assumes that, say, the norm of our b, or beta hat tau, it must be equal to 1. Well, then we get this Minsky estimator. Well, there's actually, the estimator by itself is actually quite nice, but we should realize that, unfortunately, this estimator has a very low rate of convergence. The convergence rate is only equal to n to the power 1 over 3. And that's low in econometrics, because you should realize that the standard convergence rate is square root of n, so n to the power half. The problem is that at the moment that the convergence rate is so low as we have over here, so lower than the square root of n, then a lot of things that we usually do in terms of econometrics can no longer be done. For example, taking bootstraps cannot be done at the moment that the convergence rate is not equal to the square root of n. So in that sense, this is actually not such a nice estimator, because we cannot calculate, for example, the standard errors based on, say, this low level of the convergence rate. Therefore, Horwitz came also in the Journal of Econometrics with an adaptation of the original Minsky estimator. And what he does is that he doesn't, maximize the criterion function that we had before, but he's going to maximize this criterion function that we're over here, which actually has only one difference, and that is that the indicator function that we had in the previous slide, so this indicates the function that we're over here, is going to be replaced by this k function that we're over here, which is evaluating xib over hn. Here k is going to be kernel smoother. Now I'm pretty sure that you have heard about kernel functions before. You should take into account that this is not a real kernel function. Usually kernel functions are of course related to, say, density functions, but this is actually not a standard kernel function. It's actually nothing else as the integral of a kernel function. And taking into account that standard kernel functions of course are densities, this can actually be interpreted as a distribution function. Only assumption that we actually have to make with respect to this k that we have over there is that we have to assume that kx is going to converge to 1 at the moment that x goes to infinity, and kx should converge to 0 at the moment that x goes to minus infinity. So that's the only assumption that we actually have to make. Well, we have to actually make an additional assumption, but that is with respect to hn, this hn that we have over there. Hn is here the so-called smoothing parameter that we also have in standard kernel density estimation. The assumption that we have to make with respect to hn is that hn goes down to 0 at the moment that n goes to infinity. because only in that particular case we can actually show that this beta hat tau that we've over here is then going to be, say, a consistent estimator of beta tau. And that's not that difficult to understand. And the reason behind that is because of the fact that if hn goes down to 0, if n goes infinity, what does that mean? Well, that means that, for example, at the moment that xib is going to be positive, well then, if hn goes down to 0, if n goes to infinity, well then, for any positive value of xib, this thing is going to converge to infinity, of course, and that means, of course, that this kx, given this assumption of over here, is going to converge to 1. So in the limit, if n goes to infinity, then for a positive xib, any positive xib, this is going to be equal to 1. And that's exactly what we also have over here. Well, here we don't have it in the limit, we have it always. But here we only have in the limit, if n goes to infinity, for any positive xib, we are going to have a 1 over here. Well, the opposite is true at the moment that we have a negative xib. Xib is going to be negative. Doesn't matter how negative it is. Then, if n goes to infinity, then this thing over here is going to be equal to minus infinity. And that means, of course, that kx is going to converge to 0. And that's also exactly the same thing as what we have over here. If xib is negative, well then we are going to see that this thing actually becomes equal to 0, as we actually have over there. That means that even though this criterion function over here is generally quite different from that criterion function that we have over there, well, at the moment that n goes to infinity, we have exactly the same criterion functions. That means, of course, that if we're going to maximize this, we also are going to have exactly the same maxima. And that means, of course, that even though beta hat tau that we are going to get over here could be different from the beta hat tau that we have over there for any, say, well, infinite number of n. If n goes to infinity, they must be the same. And that implies, of course, that this estimator is going to converge to exactly the same values that estimator have over there. We know that this estimator goes to beta tau. So also this one is going to converge to beta tau. So also this one is going to be consistent under these restrictions that we have over here. Well, now this is of course a good thing. There's another good thing that we can say about this estimator that we have over here, and that is that the convergence rate could actually be higher. It depends a bit on the smoothing parameter that we have over here, but what we can say is that the, say, convergence rate of this estimator that we have over here could be made arbitrarily close to a square root n convergence rate. That means not only that it's going to be higher, but we can actually also, in that particular limit, use the bootstraps. Or we can also use, for example, the delta method, because that also doesn't work at the moment that we have a very low convergence rate. This is a good thing about this estimator. A bad thing with respect to this estimator, but that actually also holds true for this estimator that I have over here, is that this, say, at the moment that we can find this maximum that we have over here, then everything is fine. However, it's not that easy to find the maximum of this criterion function or this criterion function that we have over here. Focusing on this criterion function, you should realize that even though this criterion function is quite smooth, so that's not really the problem, it does have many local maxima. And that's not that nice at the moment that we're going to maximize something, because of the fact that most, say, maximization algorithms, well, they cannot make a difference between a local and a global maxima. They're just going to look at local maxima, whereas we, of course, would like to have a global maxima. Therefore, it's usually the case that in order to maximize this, you should use, well, quite, I would say, dirty methods that try to look at global maxima, such as simulated annealing.